Welcome everybody to our new session of the Ask Tom Spatial series. In this session today, our three speakers you see here on the slide with their pictures, and hopefully you too. We will have some fun with more than 1 million points of interest from the Foursquare Places dataset. And the speaker's idea is to show some best practices for dealing with large volumes of location information. And before we get started with a brief introduction of the speakers, let me just give some information about housekeeping. The sessions are recorded and made available via the Ask Tom platform after the session. You will also find the recordings directly via YouTube, and I've provided the QR codes to directly access either the Ask Tom platform or the YouTube channel here on this slide. We will have the possibility to answer your questions, which we'll ask you to put in the Q&A box. We will answer those questions during the session. If you have any questions later on, we typically monitor two of the very common forums where people post your IT questions. Their IT questions, one is on Stack Overflow. There is a tag Oracle-Spatial, which you can use to make us aware of your question related spatial topics with the Oracle database and spatial features in the Oracle database. And of course, you can also use the Oracle forum to place your questions. And there is a forum specifically for spatial things as well. So much for the housekeeping. And now I would like to hand over to, I think, Hans, you wanted to get started, right?
I'll get started. Yes, let me try to share my screen. I hope that works for everybody. Thanks, Karin, for the introduction and everything. Those of you who don't know me, my name is Hans. I'm part of the Spatial and Graph product management team. I've been doing this for a while, so I've been on previous Spatial Ask Tom sessions as well. Happy to be with you today. And just to give you a little bit of context what this is all about and where we started and why, I actually wanted to create a presentation on how to work with large volumes of point data for a pretty long time. Basically, sharing best practices around managing points and so forth. The idea was to extend the Ask Tom session that our colleague Dan Garinger gave about 2 years ago on best practices on Oracle Spatial in general, right? And then it must have been like a year ago or so that I saw that the Foursquare dataset was open sourced, right? Back then it was only available on AWS S3. It was not easily accessible. I looked into that very quickly, and then I thought, oh man, that needs a little more research. So I basically put it aside, and to be honest, I forgot about it. And luckily, in spring of this year, Øyvind Isner published a very nice blog post on how to work with that data set, basically how to ingest the data set, how to perform spatial queries on that data set. I have the link to the blog post here, and the picture is also from his blog. And when we had a free slot in the Ask Tom series a couple of weeks ago, we basically took the opportunity to ask him if he would join us on this talk, and so here we are. Thanks, Øyvind, for joining us. Øyvind will introduce himself in just a second. He, on today's session, will give a little bit of background on the Foursquare dataset, talk about ingesting Parquet files and stuff, and then we'll cover a couple of techniques, anything from partitioning to more advanced things like parallel pipelined table functions, H3 indexes, and so forth. And Renee has spent time to prepare some demos for us, which she'll show live. So I hope it'll be a fun session for all of you, and I also hope that there'll be something new in it for everyone. Right, and with that, I'd like to hand over to Øyvind.
Hello there. Let's see. Yeah, I suppose you can see my screen now, right? Yeah, I am Øyvind Isner. I'm just an independent contractor, and I work mostly as a DBA, but I'm moving more into the development era. So anyway, that's me. So about this data set, some of you I guess remember as Foursquare. They started many years ago, and later they created this form app where people could check in and create places and tell their friends where they are. And as you see later, it has sort of lost a lot of opportunity, popularity. But last year, as Hans said, they decided to release this entire data set into the public domain. You can actually download it from Amazon. Web service 10 has 100 Parquet files, and that will take up 11 gigabyte on disk. You use this command line tool I have, and just download it to your disk. I could have actually accessed it directly from, but I didn't want to abuse Amazon Web Services, so I just downloaded to my own disk, and then I uploaded it to my object store, as I'll show you later. So the data model is not much to talk about. It's just a bunch of places with their categories. When you later put in the database, it looks like this. 3 levels of categories, and you can sort of search through this. This is the places, 26 columns, but not all of them are really interesting. So yeah. So I think it's fairly easy to upload these files to the object store. You can just use this OCR command and upload the entire directory to a bucket you create in your object store. I used Autonomous Data Warehouse 23 AI, but you can of course use 19C and so on. But yeah, but there are some new use on 23 AI that makes it actually much easier to get started. So the key package here is this DBMS cloud that you use to add your OCI credential, and you can list your files in the object storage. And what we want to do is to define an external table on these files. So this is how it looks like if you want to list the files in object store. Pretty easy. And you can, as I said, you can actually access files directly from AWS, but again, I thought that would be kind of abuse, and I wanted to have my own copy, so that's why I did it this way. And in addition to Parquet files, which is the format that these files are stored in, you can also read these. I'm sure you've seen some of it. But what impressed me, how easy it is to create one external table on all these files. This is all it takes. Once you have the your credential in place, this is the whole command. This is the path to the bucket. And this is an expression to get all the files. I just have a small detail here. This is specified as a Parquet file, and this means that the schema, which is actually included in each file, it will only use the first one because the schema is the same for all the files. So that's it you need to do in order to actually access all these points. And you can run a query like this on the external table. This, I'm not showing any results here, but this actually searches for places around me. This is where I live or where I am right now. And yeah, so it's kind of very fast access to those data. And you can run a lot of ad hoc SQL on that external table to figure out what's in it and so on before you move on. You can look for data errors and stuff. Yeah, but the problem is that if you run queries on an external table like this, it's not really fast. So again, it's very easy to create a normal table. Just this statement is enough to create a normal table. And again, the power of SQL is that you can do this in an iteratively process. You can decide what columns you want. Maybe you find that you want to add some features, some new columns, and so on. And it's really easy to sort of improve the data extraction as you move along. And as I'm sure you have seen many times before, this is how you add on spatial index. It can't get any. I think I lost one point here. Yeah, sorry. These earlier, before 20, earlier you needed to figure out what these numbers were. But now that you can find actually constants in the package that, so you don't have to remember these numbers in case you didn't know about it. So again, it's quite easy to add those as a native SDO geometry type. Yeah. So this is how you add an index, and maybe you already know, but earlier you used to populate this view here before, but now that on 23 AI, it actually already does that for you. So it's much easier. So if I repeat that query on a normal heap table without any partitions, it responds in 15 seconds, which I think is pretty good for 105 million rows. So that is basically it. Just one last slide. This shows that maybe there's a reason why they open source it. Number of places created per year has gone down fairly fast. So yeah, now I'm going to hand it over to someone who can really analyze this better than I do. So,
Yeah.
René.
Okay, yeah, I'll quickly take over. Thanks a lot, Owen. That was great to give to have a little bit of background on how simple it is to ingest data from external files in Parquet files into the Oracle database, create a spatial index on that file, and actually start working. There's one quick thing. Let me just quickly share my screen. There's one quick thing I briefly wanted to touch on before we drill down into the initial analysis in terms of data quality. David, you already touched on it just quickly, right? As you said, it is a crowdsourced data set, right? It does have some level of curation, I think, from the Foursquare team, and there is an FAQ document on it. But basically, I took this little random sample of records, in this case from Brazil, and it just shows where what the typical issues are, right? You have different types of either you're missing the street name altogether, or you have different ways of writing this street name. You have Avenida versus AEV for the abbreviation. Sometimes you have the municipality, sometimes you don't. The region is a complete mess, right? Sometimes you have uppercase, you have lowercase, you have abbreviations, all sorts of things. The only thing which is pretty much always there is the latitude, longitude, and the country code, the 2-letter ISO country code. Now, for this session here, there are basically two things to note, right? We're just using this data fun, right? It's nothing. Luckily there are no business decisions that depend on the accuracy of these locations. So we're just, not really looking into data cleansing here. If you really need accurate addresses, and René will show that in a second. For example, if you want to, look at all the addresses of restaurants in a given city using that Foursquare dataset, the ultimate approach, obviously, to clean up the data is to use the geocoding service that we provide with maps.oracle.com. And the nice thing about using the Foursquare dataset in an autonomous database is that through the autonomous database, you can access maps.oracle.com with its geocoding capabilities to work with the data, and René will show that in just a second. But as I said, we just we for a data set of this size, there's no point in geocoding everything. You just want to do some statistical analysis on this data set. So if anything, then I would say you could do a quick match of the coordinates against the data set with administrative boundaries, which could help you to, one, filter out the errors, and two, make sure that the naming, like for example, of the city or the region is consistent. And then you can use that in in your analysis, right? If you're looking for suitable data sets with administrative boundaries, you can go to gadm.org, or if you want something curated, right, you can purchase the data from here or from TomTom, so that you can do a little bit of cleaning up. I would suggest that is a wonderful homework for all of you. Get the Foursquare dataset, do what Ovid was just showing you, upload the stuff, and then you can clean things up using administrative boundaries like this. Good. With that, I would say let's have a quick look at the data set with a few sort of initial queries. Renee, if you want to take over from here, can you just grab the screen?
Yes, can you see my screen now?
Yes, we can.
Yeah, super. My name is Renee Wikestad, and I also work together with Hans as a product manager for Oracle Spatial and Graph. And I will show you some queries you can use on this Foursquare data set. So I also have made a notebook for creating tables and partitionings and so on. So we will share that with you as well, so you could see how you could do all that kind of stuff as Eivind showed in his slides, but you will also have it shared in a notebook after the session. So to start with, I start with counting the number of data in the external table. So the external table had 105 million rows. It took me about 24 seconds to count that from the 100 Parquet files I have in Object Store here. I have an autonomous database, a data warehouse with 8 eCPU up and running. So it can do parallel 8 in this database as well. And for my internal table that I have made from the external table, as you see here, I have cleaned up a little bit, took away those rows that didn't have any long and latitude width. So but you could also add that on with geocoder if you want, but I have left those out. So it's a little lesser, but still 105 million more than that. And it took me under a second to count that, since I already have all the statistics on the table as well. So this is a describe of the table. The table I made, I didn't take with me all the columns from the Parquet files, but took those that I needed for do some kind of queries and analysis here. So here you see the columns I have with. And I also took the long and latitude and made an STO geometry point objects from all those X and Y coordinates. So in the next session here, I'm showing how you can use the geocoder to, for example, see if it's good quality of your data. So I was doing a select tree on different place IDs. And I saw that the region who was in those IDs was not very good. One was missing, one was the Oslo County, and the third one was a number 3. It should be, if I go to the geocoder, see the region for this place should be Oslo. So here is an easy way to clean up some of the data if you want for an area, or if you see there's a lot of rubbish in the data. In the next, and it took me nearly 3 seconds to do this select that I did here. In the next one, I'm showing you how to do reverse geocoding. So, for example, if you have the coordinates, then you could have back the JSON results from the geo coding, and then you could see what's should be the data for that area. So,
and you can see that there's a lot of detail coming back, just in terms of not only the closest road, but also an estimated street number. Coordinates, of course, were already the input, and the settlement, the municipality, all of that. So that is pretty comprehensive, but you don't want to do that on like 100 million points.
And what I'm sharing in the next select here is how to take out some of the data from this JSON value that you have here. So I'm taking out, for example, the country, the municipality, and the postal code for an area. So you see those is what I'm taking out from this select. It's only to showing how to use these JSON values to take out data from a JSON result. And in the next select, I did I stood within distance from a point. So I took one point. This point, since I'm located outside Oslo, this point is also located outside Oslo in Norway. And then I find those other points who was in a distance of 20 for this one, so 20 meters or so. There, as you see, there I have many of them have the same coordinates and the same address, nearly here. So it was 5 points that was the result of this. But as you see, the query was not. Took me 9 seconds to do this query from, but then it had to go out to this geo. No, sorry, this was from the table. So yeah, and doing the analysis. And the next select I did, it was to find out how it was with categories, because for each place here, as you see, this bagel and juice place is connected with the category table with more than one category. In the category table, we had around, I think it was around 2,200 categories that was in the category table. But as you see here, for this place, it matches with 3 different categories. So it's important to know that the category is a JSON string and it could be more than one category that's connected to one address. So in the next one, I show you how to take out the first category, for example, but often you don't only need the first one, you need the everything. So in the next select here, I show you how to do to find out how many categories there are to using the size together with the JSON value. And in the next, I'm using a JSON table to take out each of the categories. So here is a select to show you how to take out each of the category for one of these place IDs. And those 3, it looks like they are similar, but if you go into the numbers here, you will see if you go not the 4 latest one, but the next one, there is not the same numbers, so they are different. And I will show you also how to use this. That's the reason why I'm showing this JSON first. So after that, I wanted to find how many places was located in Norway. So out of those 105 millions, around 300,000 was located in Norway. I also did that select on the external table to see how long it took. It took me 12, nearly 13 seconds to do it on the external table, but on the table in the database, it took me under a second to do the count there of how many places were in Norway. And since I'm using partitioning, I could see it from here. So yeah, so for doing the next, I think, Hans, maybe you want to do the rest before I go forward?
Yep. Okay. Then I'll explain a little more. So now that we have a bit of a feeling for the data set, let me quickly share my screen again. Here we are. Right before we go into the details of the processing and the analysis, I wanted to share a few sort of best practices, tips and tricks, and so forth, so that we have a bit of a basis. I actually wanted to start with 3 very general hints before we go into any level of detail. And the first thing which you should always do in your database is to set spatial vector acceleration equal to true. That is a hint which is important if you have a database older than 23. In 23 AI, it is the default, but older ones, if you did have the license, you would still find folks who run this with false, even though you are permitted to set it to true, and you should set it to true. So that's the first thing you should do. Second thing, also pretty much a no-brainer, make sure all geometries that you have in your analyses and in your database are valid, because otherwise you may end up either getting wrong results or things taking longer than needed. That's also an important aspect. For points, it's not so crucial because points are easy in that respect, but there's so many geometries that we want to compare things against and so forth. Make sure that these polygons and whatever you have are valid. And the third recommendation originally was, if you have number crunching you want to do, buy an Exadata database machine. That, of course, wasn't always quite the serious stat, but no matter what, these days it's become much easier, much more cost efficient. You just use a cloud service based on Exadata, and then you're all set. And that's what we're using here. As René was saying, we're using an autonomous data warehouse for the testing, and that gives us pretty good scalability. Good. So these are the 3 no-brainers. That was easy. Then one more quick thing. When we're talking about point data, there's one thing that would actually be useful to help the database to keep the data set clean, and so that is to let the database know that a given data set only consists of points. You can set layer underscore G type equal to point when you create the index. So that essentially constrains the data in your table to points. All right, then you can be sure it's only points in there. That's the one thing I wanted to mention here. The second thing is a kind of special case, which is if you have moving point data. So if you have an application that does tracking and tracing, you have streaming data coming in from GPS devices all the time and stuff, then in that case, the artery indexing that we're using for spatial data in general is not the optimal choice, right? Technically, if you look at that, you may end up with different processes competing for the root block of the index, which can impact your scalability, at least from a certain level of load on. And to mitigate that risk, we have actually built a spatial index a couple of years ago that is not based on an R tree. And it's a regular B tree, just a regular B tree on longitude, latitude. And that's only available for point data. To the outside, that looks just like any other spatial index, right? You run your within distance query and everything works as before, but under the covers, it is actually a B tree. Now, a B tree, creating a B tree on 2 number columns here is a lot less compute intensive than creating an R tree, right? So the index creation is very fast. That's the one difference. As they're all spatial functions and everything are available as before. And the response times are also pretty fast, but the response times are not quite as fast as with an R tree. So in our case here with the Foursquare dataset, right, we have a static point dataset. So there are no updates to the POI table, no updates on the indexes or anything. We just use the regular R tree in our examples. But as I said, if you have moving point data, if you have a lot of updates to your ptree_index equal to true, and that'll be it. As I said, we don't need this here. Good. So much for the intro. Now on to the serious number processing, or a serious point data processing, right? Because all the things that I've said so far, they apply to your data set, no matter if you have a small number of points or a huge number of points. Here, in our case, if you have more than 100 million points, then one powerful technique to deal with this kind of data is to use partitioning, right? I don't know if you've been looking into partitioning, but what it is, it's basically the possibility to split your table, which still remains one logical object, into a more or less large number of physical tables called partitions underneath. Right? And on all of these individual partitions, you can do operations either collectively, do a select star and everything, and it goes through all the table with all its partitions, or you can operate on these things individually, right? To the application, doesn't make a difference, and so from that point of view, it is easy in terms of application. How would you decompose such a large physical table? Well, that basically depends on your use case, right? If your typical query or your typical analysis that you want to do on your data set is, for example, related to time ranges. Always give me the data from the month of September, and then not take into account previous months unless you do some report or something. Then it would make sense, for example, to do partitioning along the line of time ranges. Or you could do partitioning on the basis of country if you always, or typically have the country as a predicate in your query. Or you could, partition on category, right? Maybe a quick remark here, right? Other databases, they also claim that they have partitioning, but usually, if you look at it in more detail, this is, in their cases, a very manual process, right? While here, this is really pretty automated. The only downside is it is a license option, so it's not included in all databases. Luckily, we're using an autonomous data warehouse here, as I said, and in that case, it is included free of charge. There are different kinds of partitioning which are available. So you can, for example, partition by range. That was what we already had very early on. So you can say, okay, all data from the month of January go in this partition, February in here, March in there. You can have list partition, which is what we're using here, right? You can put all the data from Norway in one partition, all the data from Sweden in another, all the from Denmark in a third partition, and so forth. Very elegant is interval partitioning, where you say, okay, I have monthly partitions. All the September data go into this partition, and then once the first data set from October comes in, the database realizes, oh, I haven't seen that one yet, and it creates a new partition and it goes in there. Hash partitioning goes across all partitions if you want to distribute the load, for example, and you can combine these things.
Hans, can I?
Yes, Kai.
interrupt?
Yes, absolutely. Yeah.
It's always hard to interrupt.
It is. I'm sure it is. Yes.
So Heike has a question. She raised her hand. Heike,
oh,
do you want to unmute yourself and ask your question? What do you prefer?
Or put it into the chat, whatever, in the Q&A, whatever.
Yeah.
I'll be happy to take questions.
Okay. So.
And occasionally I'll stop.
Okay.
So, question?
Heike, just.
If not.
No. Okay.
Fine by me.
Yeah.
No
put
worries.
it in the Q&A or reach out.
Okay. Anything else on partitioning? Did I skip anything, forget anything? If not, let's move on. Just quickly, right? What are the benefits? Obviously, rather than having one huge table with lots of data, here we are splitting up the data to make things more manageable, meaning you can operate on individual partitions. For example, if you want to move things to cheaper storage, or if you want to split a partition or merge a partition, archive a partition, whatever. And because you can do all of these things online, that is also beneficial for the availability of this thing. But for us here with the large data set, really the key things are performance. So there's two important aspects around performance. One is if you do a spatial query on a partition table, then the first step that happens is partition pruning. So if there are partitions where it's clear that no data is coming from that, they'll not even be taken into account, meaning you would significantly reduce the volume of data you're looking at. And for the remaining, you can use, or the autonomous data warehouse in particular automatically uses parallelism, which is of course also beneficial to get performance. Now, what you can do these days to create a table with partitions is, or what Renee came up with was to say, okay, let's look at the partitions per country, right? Because typically, if you're searching for a restaurant, or if you're looking for the nearest pub or something, it'll typically be within one country. So let's assume that partitioning by country is a good idea. So we want to partition. We do want to do list partitioning by country, right? We have this 2-letter ISO code with the country inside. Let's partition by country. Well, we don't need all whatever 200 and something countries. In fact, I think there were 6 points of interest in Antarctica even. So the Foursquare dataset is actually pretty comprehensive. We don't need a dedicated partition for Antarctica. So the idea was, let's look at how many points of interest we have per country. And so Rennie did a quick count, grouped by country, and then ordered, of course, starting with the big ones, starting with the US at the top. And so you can see the numbers here. Now, how can I create a partition table from this information? Well, these days, just go and ask your favorite large language model. Right? So what we did was to create a prompt, something like, show me the syntax for the partition table, here's the list of country codes. Give it the list of country codes. We gave it like 30 country codes.
I gave it the 25 biggest country codes, and I added a few more that I wanted to use myself, as Norway and Sweden and Denmark. No, Sweden was with those 25, but not Denmark and Norway. So those I added on the list, but that's the list I gave the chatbot, yes.
Correct. And the result, maybe you want to say a few words about the result as well?
Yes, the result was quite nice, as you see here. It's gave me the list with all the countries I had there, and I also asked for a default at the end, and that was what it gave me as well, and how to do the select from the table as well. So yeah, it's was nearly nothing to change on the result from the OpenAI GPT 4.1 as I was using here. So let's see.
Yeah, I found that pretty impressive. I mean, in the old days, we would of course, select the country and the strings around it to do a create partition and then copy things together. And so here, this is really dead simple. I was quite impressed how well that works. So that's the one thing which we did to create the partitioned table. The other little trick which we can propose here is the following, and I think I omitted the fact that we are recommending local indices on partition tables for spatial data. I had a slide on that. I think I had it on the slide. You may have noticed that when I was talking about partitioning earlier on, right? The recommendation for a spatial data is actually to use to create local indices per partition rather than a global index across everything. And if you want to do that, the recommendation is to actually not do the whole create index statement across all whatever millions, billions of points, whatever you have in one go, because there's at the end of the day, there's the risk that things go wrong, and then after 2 hours of processing, maybe you need to restart the whole thing. The suggestion as a kind of best practice is to create the index as unusable to start with. That's the first statement here. That's the index across all partitions. Here we go. Right, local unusable. That just creates the metadata, and when you have that, then you can actually create a set of scripts that create the indices per partition. You can run these scripts in parallel if you want, so that if things go wrong for whatever reason, then you can actually just restart. The nice thing about the autonomous data warehouse is it actually does a whole lot of parallelization automatically. It does all of that magically under the covers. Your database at home may behave differently if it's not an autonomous database. So you may want to have a look at whether and how you would control the parallelism. What we had a quick look at here is loading the data. Renee, do you want to say a few words about the load?
Yes, that was with the MySQL developer. You have this real-time SQL monitoring so that you can use. But as you see here, when I was loading data, it took me from the external table to the other table. It took me 5.9 minutes to do it, and I did it with the parallel degree 8. So since I had 8 ECBUs with this database, and you can see the load was shared between all of the parallel process here in very well. So yeah.
Good point. So if you look at that down here, it really looks like it was keeping the database nicely busy, right, across all 8 processes. So that works pretty well. Right. So with that, I hope we've shown everybody how to load the data through external tables. We did the partitioning, we did indexing. Now, if during the there's one quick thing which we may want to mention at this point here. Right? If you have a connection to an autonomous database, don't use the connection low because that suppresses parallelization. Right. You want medium or high if you want to do something like this. But that aside, what I wanted to talk about next was, we've now loaded the external table. We've used, create table as select. But what if we want to perform, say, more or less complex transformations during loading? Right. For example, if we wanted to extract only those points which are inside, let's say, the city boundary of Oslo. Right, where we're not looking at the city name because we've seen we can't rely on the city name. If we wanted to do this when loading from the external table, that has basically 2 challenges. 1, the external table doesn't have a spatial index. And 2, normally a function call, if you do some kind of processing, you do a function call, then that returns a result only when it has processed all the input data, right? Which means it blocks the further operations, and it requires a lot of temp space also because it accumulates results as it goes along. So to address these challenges, what we've done is we've created a dedicated function we call STO_point in polygon that works only with points where we're checking whether something is inside or overlapping or whatever a polygon. And that function operates on a stream of input locations, right? So you have points as input locations, and it also emits a stream of output data, and it creates the necessary data structures for the spatial queries on the fly, right? The function is based on what is known as pipelined table functions, right? And in our case, it's also parallel enabled, so making it really a parallel pipelined table function. And what it does is it reads from a stream. So in our case here, it's location data coming from a cursor, but it could also be a queue or could be another function. It processes the data, so it determines is that point inside of the city boundary. and it sends the result to an output queue. And that's important, right? Technically speaking, that means inside the PL/SQL function, it uses the pipe row command and then sends it to the pipe. And then it moves on to process the next record from the stream and the next and the next and the next and so on. That technique is something which is not specific to Spatial in any sort of way. It's, in fact, it's a popular technique for data warehousing, in particular for ETL, because it allows you to build pipelines of several transformation steps, right? And you don't have to store the intermediate results in between, meaning you don't need all that temp space, and you don't have to have the next function having to wait until the previous step completes, but you have these records flowing through the system all the time. If you want to read more about this, what I recommend is having a look at the data warehousing guide. It's one of the regular Oracle documentation guides. That is useful literature. In this case, that SDO point in Polygon comes with two different signatures, right? One is for working on input streams with X and Y coordinates, which is what we have here with the external table. The other one is operating on SDO geometry. So you can actually use this function quite nicely also, not only on your external tables, but also on regular tables of views. And Renee, I think you have a little demo on how that works.
So I will try to share again with you. So back to my notebook, and yes, I started with the counting. I say it was only under a second to count everything in Norway. But what I did the next here is to check out a table I have with a polygon it's the area around Oslo, so it's the Oslo municipality. So here is my table. You don't see the geometry, but if you want to see the geometry as well, it's many points since it's a big polygon, but then you could also use this function here to take out the points from the polygon and look into those. Then I also counted the number of places in Oslo from my SDO geometry tables. I was using this SDO point in Polygon to count how many of the places in this table was in the Oslo municipality polygon. So as you see here, it was 58,000 points more than that in the Oslo area. And after that, I counted also the same one in the external table. And if you see, it's not so easy to see, it's very small, but it took me 3.3 seconds to do this SDO in Polygon from the internal table, and from the external table, it took me 27 seconds. So it was not too bad either from the external table to do the same. As you see with my internal table, I was using the geometry. With the external table, I was using the long and the latitude column from that table instead. So this showing those two in difference. And what I did next, I was also using this SDO point in Polygon to find some information about places in Oslo. Here is about every, but I only took the 5 first ones, so I took some data from that. But what's maybe more interesting is to using in different kind of queries where you want to find something special. So I wanted to find which Irish pubs do I had in the Oslo area. So first, I took this select, but as you know, when I was talking about the JSON string, to do this with taking the first and using JSON value here, this gave me only checking with the first category ID. So this gave me 8 pubs, Irish pubs in Oslo in 2.5 seconds. But in the next one, I took everything because I had to use the JSON table instead to have everything. So here I'm using the JSON table. So I go through all those categories in the JSON string, the categories IDs, and then I find out which of those was Irish pubs. And since some could be a bit small, uppercase, lowercase, or whatever, I was using also this function upper to have everything in uppercase when I did checking. So, and as you see here, then I find out that there was 10 instead of 8 so it's important to go through everything in a JSON string if you're is going to check that. So, and also taking out the coordinates for the points if you want them. So that's what I was using here, this function STU2 VKT geometry to show it here. Normally, if you use SQL Developer and so it could show geometry, but in these notebooks, you need to take out in another format if you're using the notebook here. So
that was a nice example. Nice example also of showing how to deal with the JSON table. So you're basically joining this to the JSON table, which is created from the 3 or more, or 2, 3, 4, whatever number of categories on the different objects. So I found that pretty powerful. Yeah. So yeah. Thanks.
Yeah. So I think do you maybe have a few more slides before I do the next part, Hans?
Yep.
So
yeah, I have a few more things I can go over quickly. So thanks, Renee. Let me just quickly share my screens again, because that brings us sort of slowly towards things like more analytics. Right now that we've basically prepared the data set, we have had a look at the quality. We've extracted a few things here and there. If you really want to do analytics beyond the typical within distance or nearest neighbor type of thing, so for example, if you want to do statistical analysis on point data, what you will typically need to do is to aggregate the data in some way, right? To get to meaningful comparison. And the kind of aggregation obviously depends a lot on the use case. So you could, for example, aggregate by administrative units, or you could aggregate maybe by postal codes. But then all these areas would have different sizes, or they'd be complicated in shape and computationally expensive. So for many other use cases, what particularly in spatial statistics folks typically do is they map point data to a grid, right? And we've got a couple of built-in functions to help you do this. One of them is the linear key function that basically takes a key as the it takes a point as the input, and then it returns the quad tree tile it folds into, just like you can see on the slide here. Those of you who've been around with the Oracle database or the spatial technologies in particular, you will remember the times when we were using spatial indexing based on quad trees many moons ago, and we've long since moved to R trees, but the quad tree functionality is still useful for these types of purposes. For example, if you have, where's my pointer? If you have a point that sits in here, right, then the SDO linear key function would return this cell with this ID as the corresponding cell, and you can aggregate everything that fits into that cell. If you have a point that falls in here, you can see, okay, cell IDs are relatively close, so these points are close, and so on. It's fast. It's easy to work with. A nice function to help you to basically compare your spatial data sets, or even join disparate data sets. Now, the quad tree tiling, as I said, is fast, but it also has a couple of drawbacks. If you look at the size of the tiles and how they behave more towards the poles, it is problematic, and the distance between the midpoints are also not constant. So what has become more popular these days is to use hexagonal cells instead of rectangular tiles, like the ones you can see here, right, where you would basically map point data like here into hexagons. and then aggregate per hexagon. The reason why this is so useful is that you get a nice complete coverage of a spherical object very easily. That system of hexagonal cells which we're using here, the H3 indexing, is something which was developed a while back by Uber and then open sourced. Right? It's basically a global grid, a hierarchical grid that covers the entire planet. And just like in the case of the rectangular grid, it basically maps coordinates to cell IDs. I think you can use that to aggregate things, hierarchically. You can associate different data sets like you can in the linear case. And the advantage, if you look at how this represents the shape of the sphere, is that all the neighboring cells are always equidistant, right? So you can use that quite nicely. And the Uber guys, of course, need that a lot to analyze movement, for example. So pretty useful. As I said, you can use that to join disparate data sets, right? You have one data set with, I don't know, your customer locations, you have one data set with your competitor locations, and then in order to do any kind of meaningful difference calculation or whatever, you map this to the grid, and then you can do the computations on the grid cells. And for H3 indexing, we've actually included a bunch of functions that help you to work with this kind of data. That is functionality which is actually new in 23AI, right? Given a point, you can compute the cell ID. Obviously, you can use that cell ID to compute the cell geometry, or also the cell center point, or there's even a function that allows you to take a point table as input and the maximum resolution, and then it creates a H3 summary table. It kind of persists that aggregated summary table, and you can even use that summary table to generate vector tiles straight inside the database. So as I said, there's a ton of functions in the SDO util package that you can use to work with this. Now, in order to make it easier for you, we've actually built these things into Spatial Studio. And Renee, maybe you can show us quickly what that looks like. Can you just grab the screen and then
yes, I will try to grab it. So luckily I have Spatial Studio instead of using SQL here, because for Spatial Studio, if you go for the table, for example, with my table here, Foursquare Geom Scandinavia, for example, I could go into the table and look to prepare. And if you go to prepare, you can create the HG index directly from here. You could have a different kind of summaries, but I'm using count number of points, but you could also add other kind of aggregation if you need that as well. So I have already done that. So to cancel here and back to the projects. And if I open one project here, you can see how it looks. As you see here, here you can see the density of points in Scandinavia. In Scandinavia, there was a bit more than 1.6 million. 1.6 million points. But and if you zoom in here, you will see that here is 3 different areas where it's a lot of points, because I have color coding, and darker red is it's more points there. And that's are in the main capital of Sweden, Stockholm, and in Denmark, Copenhagen, and in Norway, Oslo. You see there most of the points are in those areas. If I also take with me the points, then I could also see, and if I zoom in here, I could zoom into points. But if I go away from then HG and zoom then, okay, sorry, maybe to show you, I can also show you, there is some white boxes here, and there is places where I don't have any points. So if you look around there, you see there is no green dotted in those who are white, but in the other ones there are, and on the border. And I could also, for example, look at the Oslo area if I want that, and see how many points are in this Oslo area. But as you see, the hexa polygons are very nice to show the density and so on of points in an area, and you can use that also to select and analyze in other parts as well. So I think that's what I show you for now about that.
Okay,
so
good. Perfect. Then let me just quickly wrap up. I know we're at the top of the hour, so I had prepared a few more things. So in the interest of time, I think I'll skip over those. Let me just quickly tell you that we had prepared an additional trick of using physical organization of data on disk. Maybe you can have a look at that offline in the slides. And I think also in the interest of time, we'll skip over spatial AI and OML for Pi, which would be a nice topic in its own right. We have had a dedicated Ask Thomas session on spatial AI and OML for Pi. So you may want to go back to that session and have a look at what you can do here. Because now that we have all this wonderful data, the really interesting bit is to perform statistical analysis on it, and there's a ton of things you can do with the sample notebooks. If you still want to stick around, maybe Renee can at least show you in a second how you navigate to these notebooks if you have an autonomous database at hand. And then maybe just to wrap up, here's the usual list of resources. I was mentioning the data warehousing guide in particular. Here's the link. And if anybody has the opportunity to go to AI World, here's a set of spatial sessions, and I wanted to highlight three things. Basically, one, we have a customer session with our VP of Development, Shiva Ravada, together, who will be talking about what's new and what's next in spatial, and they'll show how they use that platform for solar energy planning. So I think that's going to be a fun session. Our colleague David Lapp is on stage with Paul Parkinson on spatially aware AI agent systems. I'm sure that'll be a great talk. And we have two customers in Hassan Rizvi's database Keynote who are using spatial technologies, both Sphere and Retraced will be present on the stage there also. So Renee, if you want to just briefly, yes, Karin.
One reminder. So the next spatial session in the Ask Tom series is end of October, so the last Tuesday in October.
Good point, and I hope to see everybody there. And then maybe with that, for those who are still interested and can't get enough,
I'm going to record that part as well.
Yes, maybe Renee can at least show you how to get to the.
Someone's got a hand up too.
Yep.
I see.
Yeah.
Okay. We'll take the questions. I apologize for everybody who has to drop off, but we'll stay on and we'll take the question. Absolutely.
Yeah. And while you are looking into the questions, I could show how to navigate to the spatial AI notebooks if you want to see them. So if you go to start our Oracle Machine Learning notebooks that follows with the autonomous database, when you're logged in, you go to you have this sidebar here where you go to templates, and in the templates you will find examples, and in the examples there is a lot of notebooks both with Python, R, and SQL, but in the Python part we also have all those with spatial, and we have spatial regression, spatial clustering, and spatial a lot of different kind of spatial AI notebooks here, but and there is also some demo data that you could start with. So there is one of the notebook that you run first if you want to run all the other ones. But the way you put it into your area and to run these example notebooks, you have to click around here and say create notebooks, and then it will be copy into your project space, and then you can run it from there, and you can change whatever you want and see. But it's a very nice help to start with use and to check out how Oracle machine learning for Pi with Spatial works. So I think I stop there and you can go into the questions, Karin.
Yeah, thank you. Thank you, Renee, Øyvind, and Hans. We have taken care for the question. There was one hand raising by...
Hi, could you hear me?
Yes, we can hear you. So please go ahead and ask.
Ivan Koroc ist mein Name und ich habe ab und zu ja sozusagen kleine Gespräche oder kleinen Austausch mit Karin und Hans. Ja. Es geht um Folgendes, um Validating und Rectifying Spatial Data. Ja. Hans ist bekannt wegen einem Artikel, ja, wie soll man das machen? Aber lass mich klären, was ist meine Herausforderung? Vielleicht kann ich Hilfe von Ihnen bekommen.
Just one second, since we have moved to German.
Yeah. I will speak English. Sorry, I could continue English.
That would be very kind.
Because for Renee, it would be also interesting.
Yes. Okay.
Our challenge is because we are using Argis, this Esri product, and we are using Oracle database in background, is that we have Schwarze Group, Lidl, Kaufland. We have a lot of polygons with big areas, and the guys are creating some polygons which are really huge. That means could be dozens of thousands of points. Then we do this validate layer with context, and we get some errors. Yeah. The issue is we could try to do rectifying. We will rectifying usually, as I understood, work on the way a few points will be taken out, and the troublesome error should be resolved. The issue is we don't know what points are missing. So I could get the both geometries to compare, but I can probably have to do crazy things, maybe to put all points in some area, then from rectified geometry area, and then to compare. Why we need this? Because when we get the error, very often because of so many points, we can't find this on the map. Where is what the point is problem? The guys could look there and say, oh yes, we have here some intersection or whatever other thing, and they could then approve this rectify action. So is there
so you're looking for interactive rectification. Okay.
If we could see these 3 points will be removed, or you have sometimes a part of the solution in the error itself is saying in the ring 5 something, or whatever, but how I should find where is it place mentioned in the error itself.
Okay. Yes. Okay.
You could do this offline, if you like, just to mention what's. I tried some crazy things with verticals, get verticals and things, points before and after, but it's really, troublesome.
It's an interesting and it's a big topic in its own right, validating and rectifying spatial data. I completely agree. And in fact, when you were mentioning large areas with many points, we have some specific optimizations on how to deal with large geometries. And one example is actually Norway with its coastline that typically has many points, many points. Things like that, which we have touched on in the best practices session that Dan Garinger presented 2 years ago. So there's a dedicated section on dealing with large geometries that does not specifically cover the topic of validation and rectification, but at least you may want to go back to that. The recording is still up on YouTube or on the Ask Tom platform, so you can use that for interactive validation and rectification. We don't have a sort of a tool per se, but there's a few things maybe which we can look into, and I'd love to have a conversation with you offline and see if and how we could potentially help you with that. As you said, for certain types of errors, you get a hint as to where the problem occurs. And you can also use the spatial functions like the SD or util functions to identify where in the array that is and stuff. But of course, we don't have like Spatial Studio editing capabilities where, you know, Spatial Studio just highlights this is where the problem is. So we can have a dedicated conversation on that. I'm just noticing that my colleague David has unmuted himself. That looks like he had an additional comment to make. Is that right, David?
Yeah, yeah. This is a really good idea. I think to like not necessarily even you know, like an interactive feature would be great, some sort of interactive thing like Hans is talking about, but also just at least a programmatic way, like a declarative way to, I'm thinking potentially a more detailed validation report that most of the time people wouldn't want. But if you do, you know, then to have something like that available. So we can absolutely take this up with you a little bit more offline, and that's a great thing about these sessions. One other thing that was, I'm sure, part of Dan's session on best practices that doesn't really answer your question, but would reduce the amount of those situations. I think that you may be already doing this, but if you look at what your potentially most fine-grained tolerances that you can that is reasonable with your data, then reducing that tolerance can all of a sudden eliminate lots of validation issues, and you may end up with a much smaller queue. Now, those still need to be explained more fully, as you're saying, but we start by saying bring that resolution down as small as you can, especially with this type of like hyper detailed
I
polygon.
agree with you, but the issue is there is somewhere in documentation that let's say proposal from the tolerance is 0,05, yeah,
Right.
or 0,5. And if you go down, yeah, some of the functions are actually not, if you go to 0,01, yeah, some of the functions, it's I don't think mentioned exactly which functions are actually not going and use this really small tolerance. And this is also maybe one good topic where we don't have very much education or material, yeah, where we could learn a lot. I'm very clear with tolerance. That's my daily, let's say, discussion with my colleagues. Of course,
Yeah.
if you reduce tolerance, you could get less duplicate points and something like this. But the issue is you will still have always some amount of errors. But I need to find where is this error with XY, yeah, and then to say, colleagues, look, you draw a half of Germany in some South Germany market, yeah, and somewhere you draw something completely wrong, yeah, which is not okay. Here is this place, yeah, and then they could really make big and research to say, oh, my drawing is wrong. I have to correct it. Or I'm allowed with rectify to correct it. Yeah.
Okay.
That's the idea.
Two things we can take away. So one thing is getting back to you, following up on the discussion. And the second thing would be to have a follow-up session on Ask Tom, taking care of best practices for validating and correcting invalid geometries. And I just thought about the third thing, David, since you are our major point of contact for Spatial Studio into development, so we should check whether we will have some kind of interactive feature to deal with better logging of the actual errors or issues in when validating geometries and how to tackle these issues interactively. Okay.
Yeah, I think that's excellent. So
I'm very grateful.
Yeah, do please send me a quick note so that we can follow up. I'll stick my email address into the chat just so that you have it.
Yeah, Hans, I already sent you via LinkedIn
okay.
contact.
Good.
Yeah, so we
okay,
could
good,
exchange.
fine. So then we're fine. Then that's great. Okay, no problem with that then. Yes.
Yeah, I stopped the recording here.